Well, truly an honor to be able to come here and, there we go, to speak to you. Giselle, thank you so much for the opportunity. This is a very special Congress to me. I see Joe Dallas in the background who with me helped start AIO. There's some true pioneers in LiDAR technology here in the room. If you look at the Light the Future series that OSA has, there's some really amazing speakers that they've had since the centennial. You've got, I'm going to call them out like I told them I would. You've got Paul McManaman here, Ed, you've got Dennis Killinger. These are real, true pioneers in LiDAR. And so what we're doing is really riding on the backs of giants in terms of the technology that was developed over many, many years. Liz, Greg, thank you very much for the opportunity to come speak here as well, and the entire staff at OSA to make this happen. And really, this is what I'm going to present for you today is the result of really 350 people that we've grown to at Luminar. So if you look at the role of optics and photonics in moving people around in the future, I think this quote that I found sums it up. We're confident that the automotive industry will change more in the next decade than it did in the last 100 years. I think if Henry Ford were to come back and see what we've done with cars since he left us, he'd go, what the hell have you guys been doing? So it's pretty bad. So we're going to see a lot of change in automotive. And so let's start with the easy stuff. Let's just start with humans as drivers, and humans are horrible drivers. So you start, you got these cars, you're starting to put them, they're called horseless carriages. You're putting these things onto roads, and then you want to drive at night. What do? You use a gas lamp. So that's Photonics 1 in automobiles. But then it goes from there. And then things got really cool. You got these high-intensity discharge lamps. And then you got into LEDs. You can start really doing some interesting things with LEDs and turning them off when your turn signals go on and such. But where things get really fun is where you can start using lasers. And you can use lasers, and you can hit a phosphor, and you can convert that light from blue, just like the LED flashlights or in your cell phone. And then you can actually put either a micromirror in this case, and you can dynamically adjust where you want light in the scene. This is taking optics to the next level. Or you can use things like DLPs or micromirror devices, and you can see the patterns up there where you can adjust where you want light to go. You're going to turn a corner to the left, I want some more light there. I can use a camera system. The camera system can look, and is there a car there? If not, light it up. But if there is a car there, you can make sure that the light never gets into the eyes of the human, as you see in the bottom picture. So there's a lot of opportunities here for this. So adaptive lighting is just the start of photonics enabling the cars of the future. Now, at some point, which I'll talk about later, you're not going to be driving, the car's going to be driving. But until then, what you're seeing are these infotainment systems and these driver consoles where data is being thrown at you like crazy. With OLED displays, more than 300 million units of displays going into cars every year. It's a lot of things, and these OLEDs are enabling new applications. But let's take it to the next level. We're in the optics and photonics space. Why can't I see through my roof? Why can't I see through the hood? Well, with augmented reality, there's a lot of people talking about that here, VR, AR, why can't you see right through what the car is seeing? You've got cameras, you've got displays, you can put that through. So why not be able to both have a heads-up display that gives you information on your incline and roll, your speed, where your wheels are pointed, but also give you the ability to virtually see through that engine. This is the promise. This is what Range Rover has, is their transparent hood concept. Now, again, you've got humans in the loop. Biggest challenge I have in driving today isn't my driving, it's the person next to me on their cell phone. We've all encountered this. So being able to have information in your periphery vision, you can just look down, not take your eyes off the road to see what's happening. Who did that text message come in from? Do I need to turn left? I was rear-ended about a year ago by somebody who was down looking at Google Maps in their phone. It's a real problem. The other thing is the number of people, as these cars get more and more complex, just to change the radio station. Gesture control using optics and photonics technology, looking at things like using near-field 3D scanning is going to be a very real possibility. You can use that, you can do structural illumination, you can do stereo cameras. You're at a very short distance. Doing 3D gesture control is pretty easy. So we've got the humans, they're paying attention to the road, they can see what's going on ahead of them, or can they? So a big challenge, especially up north or in Finland in this case, is black ice. You can put optics and photonics technology into a car, and in that car you can detect ahead of you the road conditions and know whether you've got black ice, whether you've got snow, is it slush, and be able to plan ahead and apply brakes and or apply traction as needed. So we've got the humans in there, but what we really want to get to is safety. We want freedom of mobility for people. We want people to be able to get out there. And so let's look at autonomy more than just this really cool stuff like looking through your hood. Let's talk about the numbers. So frankly, humans are terrible drivers. They're really bad. In fact, if you look at the number of miles per incident that a human drives, they're very bad. So the idea is to get these self-driving vehicles out to be better than humans. That's the goal. We want self-driving vehicles so that there's less deaths, there's less accidents. So a human drives 85 million miles before a fatal accident. The problem is, at the same time in the US, if you do the math and the numbers, 35,000 people per year are being killed on highways in this country. Let me put that in perspective for you. 35,000 people. That's the equivalent of a 737 dropping out of the sky every working day. So imagine Monday, a Delta jet drops out. Tuesday, Southwest. Wednesday, United. Who in the room here is going to be getting on an airplane on Thursday? Nobody. But it happens one person or group of people at a time in this country, and we get complacent with it. 35,000 people a year are being killed in car accidents. At the same time, these self-driving cars are driving, and they're trying to drive, and they're disengaging the best program 5,000 miles per disengagement. So there's this gap between 84 million and 5,000. This gap is incredibly difficult to overcome. And the technology required to do that is incredibly hard. The best programs throwing the best technology are at 5,000. So there are small steps along the way. ADAS, these advanced driver automation systems, are that next step. And they're great. ADAS systems, you can look at the various features, forward collision warning, automated emergency braking, lane departure warning, blind spot monitoring. These things are really, really good. These things are all enabled by optics and photonics and cameras and radar. But here's the thing that should be a wake-up call for all of us. What they're saying is by 2060, okay, we're going 40 years into the future, we're going to reduce accidents by 30%. Are you kidding me? 40 years, and we're going to bring it down by 30%. I'm hoping where we have a future that's much safer than that. So these systems are really, really helpful. Forward collision warning is very helpful. Automated emergency braking, because what's happening is you may still have an accident, but they're non-fatal. And what I want you to see in the next slide is, and there's a video there, on how powerful this can be. I'm going to personalize it for you a little bit. So here's a bus dropping off some kids. Having brake assist on a car can be very useful. Did that driver have time to react? No. That's called an edge case in self-driving vehicles. That's the stuff that you can't plan for. That truck stopped itself. You can go pull this off of YouTube. You can see lots of videos like this. This is radar and camera today, soon to be LiDAR, enabling safety, and it's just the beginning. But we have a long road ahead. So if you look, and I talked about those 35,000 road deaths, the best autonomous vehicle programs are seeing 20 to 50% improvements in their disengagements year over year. 20 to 50%. So if you look at what it takes to get to at least human accident rates, much less to have 1 or 2 sigmas of improvement to make sure we're statistically better than humans, it's 25 years out before autonomous vehicles get to parity of human driving. Why? Frankly, garbage in, garbage out. The amount of data that comes into self-driving cars is insufficient to enable the edge cases, the 1%. You want to have automated cruise control, you want to have highway driving in limited cases. I'll show you examples of that, and trying to keep the human in the loop, you can do this. So, but the real power is really these self-driven vehicles. You know, there's a lot of hype around that, but at the same time, it's a very real need, real opportunity. And you can see the ADAS stuff really makes a difference, but not enough. So let's start with hard, but also easy, depending on who you ask. So driving on a highway. So the requirements for the systems that allow you to safely operate a vehicle when you're doing highway speeds, this is in Europe, but highway speeds in the US, you're going 70 miles an hour. 200 meters is 7 seconds of reaction time. So that's time for the car to react, to identify, segment, classify, route plan, and then execute that plan. 7 seconds at highway speeds. That's amazing. And that's technology that enables, we're providing that technology to go out and see 200 meters. This is an optics and photonics conference. But 200 meters is only part of it. The next question you should be saying is, at what reflectivity? What BRDF? Because if you can only see white cars, then that's not very helpful. Then there's, what's the probability of detection? You really need all 3 of these. Most of the LiDAR industry skips over those last 2. We can see an object at 200 meters. Well, seeing a retroreflector on the side of the road doesn't cut it. It's, can you see a tire on the road? Can you see a black car? Can you see a person walking across the roadway with a black hoodie on? That's the challenge. So being able to see down the highway is important. Being able to get highway, get fast frame rate, being able to put resolution dynamically where you want it is what people are asking for. But then we get to the real world. You're driving through New York City. What happens when that robotaxi, that robotaxi, that robotaxi, that robotaxi, the buses, all these cars have LiDAR? So if any of you have done LiDAR research, you've developed your LiDAR systems, now imagine that you've got hundreds of these LiDAR systems now shooting back at you at the same time. How do you handle that interference? Does your detector blow up when you get a direct strike right back at you through your optics? These are things you need to plan for in the real world. You also have a lot of chaos in these pedestrians. They're jaywalking, they're crossing where they shouldn't. This is a real challenge for a self-driving car. What the auto industry is asking for is millions of points per second of imaging. They're asking for point density that is in hundreds of points per square degree, if possible. They want the spatial resolution to make out the difference between a pedestrian and a bicyclist. The difference between a pedestrian and a bicyclist, someone who's got both feet up on the bike, are incredibly important, because one has right of way, one does not. You need to understand that, which means you need to have sufficient spatial resolution to understand that in this environment. That's hard. And you're going to have lots of these sensors running around. So let's talk a little bit about what is this self-driving thing. And you know, SAE J3016 has the taxonomy and definitions for terms related to driving automation systems for on-road motor vehicles. It's the SAE working group has this definition. I'm going to give you my version of what self-driving really looks like. Self-driving, level 1, feet off. Anyone here has cruise control? Show your hands. Congratulations, you now all have self-driving cars. So what this really means, level 1, is individual features like automatic cruise control and such, but in a silo. You've got one feature. That's a level 1 self-driving car. Level 2 is hands-off. This is your automatic cruise control and your lane departure warning or lane keeping. But you have to have two of those things at once. It allows you to take your hands off the car, off the wheel, take your feet off. You have two systems going, but you better be paying attention because it's temporary. Then you get to level 3. Now, level 3 is where you have a systematic automation. You've got something going on. The human is still responsible for the driving of the car in level 3. You're taking your eyes off. You're reading your email. You're doing your text messages. But you need to be prepared in a moment's notice to take over. This is where some auto companies are completely skipping level 3 because it's a liability minefield. Who's in charge? Level 4, this is mind off. This is this person sitting back, closing their eyes, taking a nap. Level 4, the vehicle is responsible. Typically, this is geofenced. There's a human outside the loop, but the human is required to take over. The car will get you out of that particular situation. If there's something going wrong, it'll get you out of that situation, but then require you to re-engage and drive the rest of the way. This could be a highway autopilot situation. Mind off is true autonomy. This is what people are really talking about for self-driving cars. And the fun holy grail that we're a ways away from is the vehicle is responsible for you and your safety, and there is no way for you to re-engage and get back. This is level 5, automation, no driver. We're a long ways away from level 5 for quite some time. So I mentioned level 3 is this interesting place. It's also a very dangerous place. Most of these systems that are deployed today are using cameras and radar together. They conflict. Radar has no spatial resolution. Radar cannot tell the difference between a big red flashing fire truck and a road sign on the side of the road. It can't tell. So if it's not moving, the radar may throw it out. That's very, very dangerous, results in situations like this. More importantly, because it's level 3 autonomy, the human needs to be in the loop still. It needs to be paying attention. So Cadillac has a great system where they actually monitor your gaze, and they make sure your eyes are open and you're looking out on the road. You have to do things. You want to make changes. You want to touch the wheel. Like Tesla monitors wheel interaction. So there are limitations for what's happening when you use just cameras and LiDAR, which presents an opportunity for this community, which is where we go to next. This is really great. There is a LiDAR system being deployed in the Audi A8 for level 3. They call this their AI traffic jam pilot. But it only works up to 37 miles an hour. This is for traffic jams. You're in bumper-to-bumper traffic, and you don't want to have to be constantly changing lanes or hitting the brakes and adjusting. This is what level 3 looks like, but 37 miles an hour is not very helpful in a lot of cases, especially for highway driving. There's a lot of cases where if you're going only 37 in a road environment, that would be bad. But it's a great start. They want to see further. They want to see further. The reason they can't see further is they don't have the technology to get there. So the key to changing that is LiDAR, high-quality LiDAR. But if you look at LiDAR and you look at the technology that went into the Urban Challenge in 2007, and you look at this system 2007, you've got a spinning bucket up on top, spinning around, giving you 64 lines of data. Very limited range, short range LiDAR, but it was incredibly useful to be able to do that. The challenge that I have with LiDAR technology as an industry is the fact this was 2007. Fast forward 10 years. Technology didn't change. I find that fascinating, that the technology didn't change in 10 years, and self-driving vehicles were using the same buckets up on top of cars. Luminar, we hope to change that. So this is an example of the TRI concept vehicle. It's got our next generation sensor on the roof of the vehicle, 4 systems providing overlap over the 360 degrees, seamlessly integrated into the car. It's also got camera systems. It has radar, side-looking radar. This is what the future of autonomy looks like. You don't have to have those large buckets up there, and we've got a lot of improvements. This system can see dark objects out past 200 meters, has high spatial resolution. And let me give you an example what a car that uses this type of technology can see. So if there are people in the room that are used to point clouds, where you can see that truck right in the middle that we digitally zoomed in. This is a single frame. It takes a second to acquire. But this is in our what we call our 1 Hertz mode. This is the point cloud. There's the truck out there. There's the pedestrians out there. And now we're going to digitally zoom out because we can walk through this point cloud. This is the level of data fidelity that LiDAR can produce if properly designed and engineered for this specific application. This is the technology that gets you out of the edge cases. This is the technology that you can use in this mode at 1 Hertz to provide ground truthing for a self-driving car. One of the largest challenges for self-driving cars is they don't know where they are, especially with GPS bounce in an urban environment. The other thing that you can do is you can look at this pedestrian. We have the ability to dynamically control where the resolution goes. So we can dynamically put more lines on the horizon and take these lines and say we want more spatial density here dynamically. And you can see the person in 3D in a point cloud. Now these colors that you see, these colors are there for you and I. It's just to be able to visualize this. You can clearly make out the cars, you can make out the human. You can come and look at this point cloud from top down and look at the point clouds and say what's happening here. But let's really show you what's possible. It's being out to sea out there. That's the 7-8 seconds down the highway you really need to be able to make decisions. This is what allows you to do route planning. This is what allows you to make sure that you're operating the safest way. And if you notice, if you look at what we have here, even when we digitally zoomed in before, we always watch out 120 degrees. Our sensor always is looking out 120 degrees. It's doing that for one reason. We never want to miss a child walking out between 2 parked cars. It's really great to say, oh, nothing's going on over here on this side of the room. So we're going to look over here because there's some dynamic stuff. We're going to take all of our resolution and we're going to digitally look over here. And we're going to get higher resolution here and stop looking on this side. That's when you have self-driving, the video I just saw you in edge cases, you need that information. So if you remember, I was talking to you about that busy, chaotic urban environment. We had cars and people. This is one of those examples. Look at all the people walking around. Look at the people walking or biking in the roadway. You have 2 pedestrians, not one, those are 2, with spatial resolution to see the 2. You've got buses, you have cars. This is Regent Street in London. Imagine having to do this with just a few lines of LiDAR data or cameras. You're doing this at night. You've got high beams coming in at you. Your cameras don't have the dynamic range to work well. There are a lot of self-driving car programs where these programs only operate during the day. They don't operate at night because their disengagement rates go up. They haven't figured out how to do that. When you're able to provide a sensor with this type of spatial resolution, range, fidelity in terms of depth, and see those bicyclists swinging through, when you do that, the LiDAR sensor inverts the sensing object classification segmentation pyramid. Typically what happens today is that, I guess it's typically, every program's a little different, is that the camera and LiDAR are the primary sensors in a self-driving car. The LiDAR, because of the poor quality, has been a secondary sensor. When we work with our customers and they deploy LiDAR systems like this, they become the primary sensor in the car. So this is a Light the Future series. Let's talk a little bit about the future. And what is life like with autonomous vehicles? So we have a little bit of catching up to do. They've been talking about this since the 1950s. Now first, playing board games, I don't know who does that much anymore today, but playing board games in a car, you're not paying attention. We can do this. This can be the driving environment. We've come full circle from the 1950s. The cabin experience is incredible. The ability, you can sleep. You want to drive from Orlando to Atlanta, why not do it overnight? Sleep on the way. You can do theater experiences. You can watch a movie on your way to Miami. You can do a video conference call and work in a work environment. In a car, you can just play games, be in movies. And then as you change the fact that there is no steering wheel, there are no brake pedals, there is no gas pedal to hit, you can get some really funky user environments. This could be level 4. The car, level 4, gets you to the safe point after a situation comes up, and then you drive the rest of the way. This could be an environment here where you drive yourself onto the highway. Get on the highway, engage self-driving, you're done. You stop the next time you need to go to the bathroom. This is what the future looks like in mobility. In addition to the future, this is just, cars like we're talking about today. But we can ignite our imaginations on design and change how we transport people. But also, what happens when you're getting to an intersection, you're about to step out, you look out, you want to make eye contact with the driver to make sure the driver sees you. Did you see me? And there's no driver there. How do you communicate with a self-driving car? Does the car see you? So there are ways that you can interact with humans. There can be signs, there could be LEDs, there can be heads-up display, or for the cabin people to acknowledge it. There's lots of things you can do to acknowledge that. More importantly, there's really cool stuff you can do in these cars where there's a pizza delivery. Why does it have to be a big car? You can go through and figure out what route this is, and frankly, that doesn't even need to be a windshield. Say this is the ride-sharing car that you're on. You can have displays inside and outside, and of course you need to do vehicle-to-vehicle signaling. We want to enable new economies with this. You want to get your groceries delivered. You want to get food from the grocery store. Today they do that. There are services that do that and drive for you. Could be getting something from the pharmacy, or it could be hot off the presses, your local quick version of the newspaper, or my favorite, let's get OPN delivered this way. This also is going to have a huge impact on urban planning and efficiency. You've got all these cars, they're all automated, they're now all talking to each other. A typical self-driving car is filling up terabytes of hard drive space each day. It's a lot of data. People are like, oh, well, we'll just send it up to the cloud. It's a lot of data. Maybe we should be using optics and photonics and all the street lights are Wi-Fi, and you're handing off the data that way using optics You're going through here, terabytes of data, coordinated traffic. If you look at what I use is Waze to get there, that's using the wisdom of the crowds. Vehicle-to-vehicle communications will help solve traffic problems. More importantly, it'll allow you to repurpose areas that were parking lots or parking garages. Why do you need them? You don't own a car. So we're on roads, but why? Do we need roads? If you look at the future and look where we're going, and go back what I was talking about with Henry Ford, looking at where are we today, there's absolutely no reason we need to be using roads. There are many programs looking at finding that gap between a car and then flying. I'd personally look forward to that. There are various concepts for these vertical takeoff and landing type aircraft that allow you to have these self-flying cars. So again, with high quality optical data, LiDAR, you can very quickly get to the point where you get to a local station, it then picks you up and it flies you to the next location, drops you back off. This is the future I hope to see over the next 50 years. Uber is working on this. Airbus is working on this. Google is working on this. This is certainly going to be happening in our lifetimes. But speaking of happening in lifetimes, you often hear people talking about self-driving vehicles and it's a race. This is a race. Well, I'm in a race. It's personal for me. I'm in a race with my 10-year-old daughter. She's 6 to 7 years away from driving, and I'm doing everything I can to make sure that never has to happen. This is her with her OMG I Love Science shirt. But that's just me not wanting my daughter to drive. The reality is I'm going to teach my daughter how to drive, and I'm going to make her learn how to drive a stick so that she can. I'm going to teach her how to change a tire. But the reality is in 7 years, she may not need a driver's license. It's already happening today. But this is a little different. This is my son. My son has special needs, autism. I honestly don't think he'll ever get a driver's license. Now, he's full of surprises. You never know. But the reality for me is that at some point, I need to find a way to reliably and safely get him from point A to point B. Whether it's a group home, whether it's his job, whether it's to go meet some friends. How do we allow people to safely get from point A to point B that can't drive? If you look at how that's done today, it's arcane. I want to fix that problem. And I want to use the technology that you all have helped invent to go do that. But there's one more. These are my parents. They're in their 70s. There's going to come a time that every person goes through where they have to talk about self-driving with their parents. That's my dream. Hey, guys, you don't need the car. You don't need the keys. I know it was your freedom. I know you liked the new car you bought last year, but it's just not safe. Or you can start with small steps. You can say, hey, how about you just drive during the day, but we send the self-driving cars for you at night. Start with small steps. I don't know anyone who wants to have that conversation with their parents about taking away the keys. This is a much more elegant solution. It's a much more safer solution. So being able to make this a reality is a personal mission of mine. And it's the same for our team. We have team members within Luminar that are legally blind, that will never get a driver's license. They are phenomenal engineers, some of them. One of them is in automation and does our manufacturing engineering. He's legally blind, and the irony is that he's helping us build self-driving vehicles to provide the eyes for self-driving cars. We take this very seriously. Safety is our #1 concern. Some of our partnerships with Volvo, our partnerships with Toyota are helping to address that. With that, I really want to thank the organizing committee. Giselle, thank you, and Joe and others that are here. Thank you for giving me the incredible honor to come speak to you today. I also want to thank Fabian Ofner, who's got these beautiful artist renditions and basically exploding cars. With that, thank you very much.